We're going to continue our discourse on signal processing, these lectures series. This is the 7th in a series of lectures on beginning concepts of signal processing. And we're going to pick up where we left off. The last lecture we talked about discrete LTI systems, discrete linear time invariant systems, and some of the properties and how we can construct solutions for that. And in this lecture, we're going to come back to the concept of linear time invariant systems and thinking about it from the perspective of continuous signals. And so the difference between the two is the discrete version. You actually do a summation over fundamental kicks to your system, and the corresponding part of that in the continuous case is that sum gets turned into an integral. And so we're going to show how that happens here and show this limiting process so we can construct solutions in the continuous version very easily. Again, everything's going to rely on these two properties here, linearity and time invariance. Linearity says I can take solutions, add them together, it's still a solution. So when we integrate over our solution space, we are actually integrating all these solutions together, and since I can add solutions is still a solution, that summation will work for us, or that integration will work for us. The time invariance says that no matter where I kick the system, the response is the same. And that's a really important property as well. If that did not hold, you'd actually have to know what the response was at all moments in time, so that as you go forward to try to construct the output, you would have to understand how that system changing is how the output is changing as you kick it at different time points. But here, time invariance is going to say it's the same output no matter where I kick it. Okay. Concept of linear superposition is critical here. It means I can take solutions, add them together, still a solution. And that is the basis of almost of all of our linear methods that we think about for solving differential equations, for solving signal processing problems. Linear superposition is one of the most important concepts we have to work with and has been sort of the basis of making a lot of technological process as we build systems such as this so that we can capitalize on this linear superposition. And that's really what allows us to represent the solution in integral form, because we want to be able to add solutions together and still have a solution. So let's go to the continuous time case. Continuous time LTI systems, we still have to figure out how to deal with the delta function. The delta function is this very important object. It's a finite kick, and we look at its response. We've already done this for the discrete case in the last lecture, and now we want to do this for the continuous case. I want to give a delta function kick, watch the response, and then if I have an input signal into my system, if I know how it behaves to a kick, I can basically sum up all the responses over all of time into an integral formulation based upon understanding how it behaves according to one delta function kick. So let's go back to our calculus concepts. And really, this is where you connect the discrete and continuum case, is that essentially, if I have a signal, continuous signal, I can always approximate this, right, as a series of steps, right? This is my discretization, as it were, of that continuous signal. And I can make each bin here, time bin size delta t, and the height of it is to whatever the signal value is. So if I want to pull out any value of the signal, just like we did in the discrete case, I can multiply it by a delta function that sifts that value out. So for instance, here, if I look at this little bin here, it's of width delta, and the height of it is the height of this signal up here. So this here is in some sense a representation of this little delta of signal that I have up here. And I can slide this over, pull out the signal at different locations just as I slide it. So the delta function is basically sifting out portions of that signal as I slide along this curve here. Okay? So that's the idea. And of course, in calculus, what we're really going to do is we're going to take that delta and take its value and take the limit as it goes to 0. And that's going to give us the continuous version of the LTI system. Okay? So just keep that in mind. This is really simple calculus. And the discrete version, one way to think about it is we go back to calculus and we don't take the limit delta go to 0. And in the continuum limit, we do take the limit as delta goes to 0. So in one case, we have a sum representation. In the other case, we have an integral representation when we take that delta go to 0. So here's the sifting property. Once again, we've already talked about this a bit, but let's just revisit it here. I'm going to specifically represent the delta function as delta of delta here. The delta is the interval where it's non-zero. So the interval is from 0 to delta, and let's say the height is 1 over delta. So the area under this object, which is just a rectangle, its height is 1 over delta, its width is delta. So as delta gets small, the width goes to 0, the height goes to infinity, but if you multiply these together, the area in the curve is always 1. Okay, so this is a very special case. We're going to take delta goes to 0, and 0 times infinity in this case is going to be 1. That's what it means to have this delta function in here. And so it only makes sense, technically, when you take this limit and this thing sits under the integral. Okay? So we've already learned that we can represent a signal, and this is in the last lecture, an LTI signal, as a summation of the signals as a bunch of sifted functions. So here, this is the value of where I'm sifting times the delta function, which sifts that value. And all we're doing here is we're going to take that sum, which we typically in a discrete system would just leave alone as a sum, but now we take this delta goes to 0 to represent this function. So this summation is going to turn into an integral. And so we're going to take this limit of this object here, and then this here is t minus k, which is k is wandering over all the values of delta t, and so this is going to turn into an integral, but now I'm actually having this integral here, t minus tau. So what I'm doing is integrating as tau goes from negative infinity to infinity, and it looks over this entire function. And of course, the delta function is 0 everywhere. So it's going to make no contribution unless tau is equal to t, and then this thing is infinity, but in infinity that sifts out the value of x of tau where this t is, which is x of t. So you see right here, I've recovered the sifting property that is so critical both in the discrete case and the continuous case. This is the most important property of the delta function, is its ability to sift out a value. All right, so just to represent this more fully, sort of in a graphical way, because it can often help, is you have some continuous signal. Here it is. And what we're going to do is we're going to think about taking some delta function here. This is a delta function that's centered right over here at t minus tau. So we're gonna look at this delta function here, and we're going to take and multiply these two functions together, which you get this here. So notice the width of this is delta. The height of this is the average value of the function there. That's one way to represent this, and that's often what you do in either a trapezoidal rule for integrals, is you take the average height of this function that you're pulling out, and you're going to multiply these two together. Okay, so you're going to sift out the value of this x of tau times a function of height 1 over delta, and so when you multiply these deltas together, they're going to cancel, and you're just going to get the height of the function itself. So in the limit, as you take delta going to 0, you're going to squeeze this into a delta function, which is going to pull out the value of this thing only at where you squeezed it down to, which is x of t. So the way we typically draw the delta function is like this. It's 0 everywhere, and right here, I draw it as an arrow. It goes to infinity. But if I integrate this, it's actually unit area under the curve. Okay, so that's the definition of the delta function. And so I'm taking this function, multiplying it by this function, and what you pull out is the delta function times x of t, the value there, which is x of t. Okay, so this is just the continuous version, and again, just trying to bring together the discrete and the continuum, and you can see I go from sums to integrals, and this is the representation, and this is how you draw these delta functions. Okay, so what does that mean for us in terms of what we had already constructed for the discrete LTI systems. In the discrete LTI systems, what we said is the output of a system, this is the Y event, it's equal to the input to the system, which is the x of k here. So as I run the signal from negative infinity to infinity, right, what I'm going to do is I'm going to sum this up times h, where h is the kick. Remember, h of n minus k. So h is the fundamental response to a kick at n is equal to k. So when I have a signal, for instance, a signal acting at time x1, the response to it, which is h1, I add it here. And then to that, for instance, if I have a signal with some value at x2, I add the kick at x centered at 2. So I just keep summing up the responses to the different input signals, and that's how I construct the output signal. Okay, so this is a convolution. This is what this is called. It's a sum over all these, where I slide this thing here from k, goes to negative infinity, infinity, and I add up all the contributions from all the kicks. In the continuous version, this here simply turns into integrals. So y sub t is equal to negative infinity, infinity, x of tau, and then here, h of tau t. H of tau t is now the response to the delta function at t minus tau. Notice here, at this point, I'm assuming that h of tau could have different responses at different times. So what we want to really do here is make h of tau the same. For a time invariant system, h of tau, no matter where you kicked it, it would give you the same response. So let's go to that case because that's the one of most importance to us. So if we say to time invariance, h of tau t, there is a fundamental response. Let's call it h of naught. So h of naught is the response of the system to a kick. It doesn't matter you kicked it at time 0, at time minus 10, time 10. Let's assume that no matter when you kicked it, you always get this response. And we're going to represent that by, we're going to drop the 0 and just say it's h of t minus tau. This is the fundamental response of the system. And we did this exactly for the discrete case as well, right? The discrete case, we also assumed there was a fundamental response to a kick. Now, once we have that, then this continuous time LTI representation simplifies just down to this. Y of t is the integral, the input signal, integrated against this fundamental reaction to your kick, d tau, and oftentimes an integral of this form where you have one argument sliding against another argument, so tau, t minus tau, this is called a convolutional integral and is often represented just by here. So this star represents convolution. It means take this function x of t, y sub t, and basically integrate them against each other with this offset of time where you integrate across each other this way. Okay? That is the response of the system. So if you're going to actually understand an LTI system, it's actually critical that you understand the response to the delta function. So if you have a function or a differential equation that dictates the behavior of the system, your first objective when you want to think about these LTI systems is to kick the system with a delta function, understand the response. Once you have that, you have the general solution, which is given right by here. Okay? So that is your objective, is understand for a fundamental system what its unit's response is. So again, for LTI systems, discrete or continuous, we have these very simple representations of the dynamics. We're making use of the sums in this, or the integrals, which is the limit of the sum. And we're just saying, put in an initial signal, ask how does a signal actually, what does the kick do? Well, it's dictated by h. And so a signal is just a series of kicks, as it were. And so if I know how it behaves to one kick, I can just say, well, a signal is a bunch of kicks. I just add them all up. Same thing here. If I know how it behaves according to a delta function, let's call it with h, then I can just say, well, my continuous signal is a bunch of kicks as well. I just integrate the response of all these, of each response at different times according to the x. I sum it all up, or I integrate it, and I get my response here. So these convolutions become super important. So let's walk through one example in particular. And last lecture I walked through one example of how this works. I'll do the same thing here for a continuous system. So two things you need. First and most foremost is what's the response to a kick? So if, in other words, I take my system and I give it a delta function kick, let's say this is the system's response. So in other words, nothing's happening, I kick it, it turns on. Okay? So let's suppose that's the response to whatever system I'm looking at. Then I could also ask the question, okay, now I'm going to put in a signal. Here's my signal I'm going to put into this thing. It's 0, and it turns on, then it exponentially decays. And then you ask the question, if I put this signal into my system, and this is the fundamental response, what is the solution to this? What's the output I read at y of t? Well, somehow, when this thing comes on, it's going to first induce this kind of response. And look, I'm going to keep adding that response, and then it's going to decay away. So initially, I have a lot of this signal I'm trying to put on, and it builds up, or I integrate on it, and then eventually I add less and less and less. The thing that you need is not h of tau in that integral, but h of tau minus t, and here's what it looks like for t less than 0, t greater than 0, and notice what happens as you bring it across here. You're going to integrate against this thing, and then you either get a contribution or no contribution, depending upon where you're integrating the signal. Because remember, x of tau, you're going to integrate against it's 0 and then has some finite values. So let's actually work this case out fully. So first of all, here is what your kick looks like, or what your input signal looks like. X of t is, it decays exponentially times u of t. U of t, remember, is 0 for t less than 0, and then 1 for t greater than 0. So that's this curve right here. That is x of t. Okay? And here we're going to assume that a is greater than 0 and real. Okay? My response to this function, is h of t, which is use of t, which I'm just showing you here. That's here. It comes on. So that is this guy here. So h of t is just 0, and then when I kick it, it's 1. So those are the two functions I need when I'm computing the integral. In fact, this is what I need under the integral, which is x of tau, h of t minus tau. So I have the x right here. I have the h right here. So I can construct these together, and you can just kind of draw these, and you can start seeing that this function is e to the minus a of t between 0, tau, and t. So in other words, as long as tau is in this window, I get a non-zero contribution. If it's not in that window, it's 0. Okay? And so that's also not hard to see from here, right? So if I'm integrating this thing, there's a place where there's no contribution, and then finally there is a contribution to this. And so this is what you get here for the contribution. So I'm going to take this function, and this is in my integrand, and I'm just going to integrate it out. So there it is. And so now when my y of t is, you integrate over all of this, for tau goes to negative infinity, infinity, and here's your solution. Okay, so this is a pretty simple integral to do. When you integrate this thing, remember that tau goes from negative infinity to infinity. Well, the only place where it's non-zero is in this region, 0 to t, so that integral becomes from 0 to t of this function. And that's very easy to integrate. And the limits are 0 to t, so you can evaluate it to get out this solution right here. So this is your output, 1 over a, 1 minus e to the minus at, times u of t, which means this is when it comes on. And this is what it looks like. So this is what the solution looks like to this thing. So what happens is you start the system off. You have this x of t that comes on, and it starts now adding signals, which is an integral version of this thing here. So first it comes on, there it is, and you add some delta amount of this, function, which means you're adding this, and you keep adding this function, right? You keep kicking it, so it keeps adding this and adding it and adding it, but now you're adding less and less and less and less. And so what you're seeing here, when I kick it, I first start adding and adding and adding, but I'm adding less and less and less. You can actually work out the closed form solution, and it has an asymptote here. So this is a very simple example, but it kind of highlights what's going on here, which is you turn this thing on, you start to integrate over that response, And here's what ultimately your solution looks like over time, YFT. So the continuous version is very closely related, obviously, to the discrete version of LTI. One's a sum, one's an integral, but they both simply work on this very fundamental premise, which is all I have to do is if I understand the response of the system, that H, in other words, H, if I understand how that system reacts to my kick, all I have to do now is look at the input signal, and every point of that input signal is going to induce a kick into the system that I just add together to produce my full solution at the end of this. So that linear superposition in LTI systems has all these beautiful properties, and they're the kind of system that you actually want to engineer in practice. In fact, in good engineering, what you want to do is set up a system and figure out, can I engineer my system and make it an LTI system? Because if you can, all these very nice mathematical properties hold and allows you to do control very nicely of that system. We'll talk more about these properties in the upcoming lectures.